Welcome to our Quantum Deep Dive. Today, we are jumping straight into the fascinating world of, well, a leading figure really shaping the future of quantum research. We're going to unpack an essay by Yurigo Schneepat that gives us an incredible window into the work of Alán Aspuru-Guzik.
That's right. And our mission with this deep dive is to, go beyond just the facts. We want to really grasp who Alán Aspuru-Guzik is and why his unique work, it's right at this collision point of quantum science, chemistry, computing, even AI, why it's so groundbreaking.
And crucially, what that actually means for you listening right now.
Exactly.
So think of this as maybe a guided tour through some pretty cutting-edge ideas. We'll trace his path a bit, explore his key research areas.
See how it's being applied, in the real world.
Yeah. Right now.
Yeah.
And look ahead to the future of this field because it's moving fast. Ready to jump in?
Let's do it.
Okay, so where does this journey begin for Alán Aspuru-Guzik? Kick things off for us.
Well, it starts in Mexico City, but what's immediately interesting, and the essay points this out, is how quickly he started building bridges between, traditional fields.
Okay.
He studied chemistry at UNAM, that's Mexico's National Autonomous University. But then his PhD at UC Berkeley, that was in theoretical chemistry, working under William A. Lester Jr.
Ah, okay.
And that's really where he began to see the potential applying fundamental quantum mechanics to solve complex chemical problems. Not just observing them, but actually simulating them.
So applying quantum ideas to chemistry problems, that feels like a pretty foundational step right there.
It really was, and he built on that pretty quickly. His postdoc at Harvard saw him focusing specifically on developing quantum algorithms, tools really, tailored for molecular modeling. So it wasn't just theory anymore, it was about designing the actual computational tools. And, that work really turned heads.
And he stayed on at Harvard then?
Yes. Became a professor there in 2006. His lab became sort of a hub for pushing these boundaries. One project that really stands out that the essay mentions is using quantum models to simulate excitant transfer in photosynthesis.
Simulating photosynthesis. What does that mean exactly in this context?
It's about understanding, really at a fundamental quantum level, how energy moves so incredibly efficiently through the molecules involved in photosynthesis.
Wow.
By simulating this with quantum mechanics, you get insights that could, potentially inform the design of new super efficient solar cells.
I see.
And he also applied this to simulating organic molecules specifically for solar cell applications, basically predicting their properties before you even try to make them in a lab.
Okay, makes sense. And then in 2018, a big move, right? University of Toronto.
Exactly. And this move, it really seemed to solidify his commitment to that interdisciplinary approach. He joined as a professor in both chemistry and computer science. Yeah, that's a powerful combination. And he's deeply integrated there, collaborating with places like the Vector Institute for AI and the Creative Destruction Lab. The essay makes it clear this wasn't just, a change of scenery, but a strategic move, aligning with centers focused on AI and commercializing deep tech.
And it sounds like mentorship and collaboration were pretty key ingredients along the way, too.
Oh, absolutely vital. The essay really emphasizes the role of mentors like William A. Lester Jr. and also Nobel laureate Martin Karplus at Harvard. Karplus apparently really encouraged him to ground his theoretical brilliance in practical applications. So this collaborative spirit, this focus on real-world impact, that became a hallmark of his research.
Okay, let's unpack his core research areas then, because they cover a lot of ground, but like you said, they're deeply interconnected. First up, quantum chemistry.
Right. So this is basically using the laws of quantum mechanics to understand and predict how molecules and materials behave right down at the fundamental level. And he's been really instrumental in making this more than just like an academic exercise. It's becoming a predictive tool, that photosynthesis simulation we talked about.
Yeah.
That's quantum chemistry in action, looking for those efficiency insights. And predicting properties for solar cell molecules. That's using quantum methods to speed up discovery, moving away from costly trial and error towards targeted design based on simulation.
And how does quantum computer algorithms fit into this picture? Because that feels like the next piece.
Yeah.
How do you actually do the calculations for these quantum effects?
Precisely. You need algorithms specifically designed for quantum hardware. And a major contribution here, something the essay highlights, is the variational quantum eigensolver, VQE.
VQE. Okay, that sounds important.
It is, especially for the kinds of quantum computers we have today. The key insight behind VQE is that it's a hybrid algorithm.
The hybrid, meaning?
Meaning it uses the quantum computer for the really tough part, like calculating the quantum interactions in a molecule, but it relies on a classical computer for the optimization part, finding the best solution.
Ah, so it's like a tag team. using the quantum computer for its unique skills, but leaning on classical computers where they still perform better.
Exactly. And that hybrid nature makes it much more practical for this current generation of quantum machines, which, are still pretty noisy and error-prone.
Right.
It's crucial for calculating things like the ground state energy of a molecule, which tells you a lot about its stability, its reactivity.
Got it.
The essay also mentions the quantum phase estimation algorithm, QPE, maybe a bit more demanding for current hardware, but it's another foundational quantum algorithm for doing highly accurate simulations, often used as a building block, maybe alongside VQE sometimes. These algorithms are really key steps towards actually using quantum computers in chemistry, for real industrial applications.
Okay. And then he brings in AI and machine learning.
Yeah.
How does that connect with quantum chemistry and algorithms?
This is where things get really exciting, I think, because it's about speeding up the entire discovery pipeline. AI and ML are just fantastic at finding patterns in huge data sets. So you can use ML to analyze the results from quantum simulations or even experimental data and predict which molecules are most likely to have the properties you're looking for, say for a new battery material or maybe a drug candidate.
So instead of simulating or synthesizing every single possibility, AI helps you make smarter guesses. Helps you narrow it down.
Precisely. He's used ML models to predict chemical properties or optimize structures way, way faster than traditional approaches, orders of magnitude faster. So this combination, quantum simulation for that atomic level accuracy and ML for speed and pattern recognition across this vast chemical space, it creates a really powerful new way to do material discovery. It's not one or the other, it's how they work together.
Okay, so we've talked about the research areas. Yeah. How does this all translate into, practical applications? Yeah. Where can you actually see the impact of this work?
Well, a major area is definitely material science, especially for renewable energies. I mean, the search for better materials is absolutely critical for things like solar cells and batteries.
Right.
And his work is directly focused on speeding that up.
Like finding those organic molecules for solar cells using simulation that you mentioned.
Yes, that's a perfect example. Predicting which organic structures might be efficient, maybe more sustainable alternatives to silicon. And for batteries, too, using these methods to analyze candidate materials. Could be lithium compounds, could be totally new organic designs.
Looking for what? Higher energy density, longer life.
Exactly. Finding materials with higher energy density, longer lifespan. I mean, if you care about electric vehicles or storing energy on the grid, this work is really foundational.
Okay. And what about in healthcare? Medicine?
Yeah, there's significant potential there too, particularly in drug discovery. Finding new drugs is just incredibly time-consuming and, frankly, expensive. Mm-hmm. Quantum simulations and algorithms can help by modeling how a potential drug molecule interacts with a target in the body, like a protein.
So predicting how well a drug might actually bind to its target.
Exactly, right down at the atomic level. This lets researchers predict promising candidates much more accurately, filtering out the less likely molecules really early on. The essay specifically mentions using quantum algorithms to tackle antibiotic resistance.
Oh, interesting.
By modeling how potential compounds bind to those resistant bacteria, trying to find new ways to attack them. This just makes the whole search for new antibiotics faster and hopefully more effective.
And the AML part isn't just theory here either, right?
Yeah.
It has very real practical outputs.
Oh, absolutely. This is where concepts like the self-driving lab come in. This is probably one of the most, striking examples of his vision.
Self-driving lab. Tell me more.
Imagine a laboratory that uses AI to actually design experiments, then it runs them automatically using robotics, analyzes the results, and then uses that data to plan the next experiment.
Wow.
Iteratively optimizing the search for a new material, completely automatically.
That sounds like science fiction.
It's becoming reality, and it's driven by his work. It's about automating the entire scientific discovery process for materials, just vastly accelerating the pace.
Incredible.
And ML is also used in battery R&D, analyzing massive data sets from experiments or simulations to predict properties like charge cycles or safety, prioritizing candidates without needing months of lab testing for every single option.
Right.
And for designing catalysts too, the things used in chemical manufacturing. ML combined with quantum insights helps create materials with very precise desired properties for industry.
Okay, so moving beyond the specific scientific results for a moment, how has Alán Aspuru-Guzik influenced the scientific community itself? What's his broader impact been?
Yeah, that's a good question. A key insight from the essay is his really strong push for interdisciplinary collaboration. I mean, he doesn't just dabbled in different fields. He's actively built research programs and collaborations that genuinely merge chemistry, physics, computer science, and AI.
He really walks the walk then.
Exactly. He shows how you break down those academic silos to tackle problems that, frankly, no single field could solve alone. And that approach, it's really setting a template for future research. And he's clearly investing in the next generation of scientists as well. Oh, absolutely. The essay mentions he's a dedicated mentor. Numerous students and postdocs who've worked in his group are now leaders in their own right, carrying forward this vision of interdisciplinary, impact-driven research. That lineage, that investment, it's crucial for the field's future.
He's also a big advocate for open science and open data, I gather.
Passionately so. He strongly believes that scientific progress benefits everyone when research is transparent and accessible.
Makes sense.
Sharing data, algorithms, methods openly, whether it's through preprint servers like ARPSIV or dedicated platforms like the Open Quantum Materials Database, it just allows the global scientific community to build on each other's work faster. You avoid duplication. You accelerate discovery for the benefit of society. It's a really fundamental part of his philosophy.
So, given all this really exciting progress, what are the big hurdles still ahead? And how does he see the future unfolding? Where's this all going?
Right. Well, there are definitely significant challenges, absolutely. We're currently in what people often call the NISQ era.
NISQ?
Noisy intermediate scale quantum. Basically, the quantum computers we have today are limited. They don't have that many qubits, the quantum bits.
Okay.
And the qubits they do have are sensitive. They're prone to errors because of something called decoherence, basically losing their delicate quantum state.
So the calculations aren't perfectly reliable yet. There's noise.
Exactly. Oh, definitely. Think about data security, for instance. If, or maybe when, powerful, fault-tolerant quantum computers become a reality, they could potentially break much of the encryption we rely on today.
That's a big deal.
It's a huge deal. Now, research into post-quantum cryptography is already underway, trying to develop new encryption methods that are resistant, but it's a significant race. Then there's the crucial question of access and equity. How do we make sure the incredible power of quantum technology benefits everyone, not just wealthy countries or large corporations?
Yeah.
His open science advocacy is one way he's trying to address this, trying to level the playing field a bit. And of course, the potential impact on job markets, the need for new skills, the urgent need to ramp up STEM education. These are vital societal conversations we need to be having right now.
So despite these challenges, what's his vision? Where does he see this all headed?
He's definitely a visionary, always pushing the frontier. He sees us moving towards more robust quantum hardware, maybe entirely new types of qubits that are more stable. He envisions developing self-learning quantum algorithms. Algorithms that, when combined with AI and ML, can essentially discover solutions to complex problems almost automatically, especially in areas like materials, pharmaceuticals, energy.
That self-driving lab concept again.
Exactly. That's a perfect illustration of this future vision, a seamless integration of AI and quantum computing to just revolutionize scientific research itself.
It really sounds like his work isn't just about building powerful technology for its own sake. It's about specifically directing that power towards some of the biggest global challenges we face.
That's the core insight, I think, from Schneepat's essay. He clearly sees quantum research not just as some niche scientific thing, but as a key player in enabling sustainable energy, developing life-saving medicines, transforming critical industries. His work shows that even now, even in this early NISQ era, progress is being made. And the potential for positive impact on humanity is just immense. Provided, of course, it's developed and shared responsibly and openly.
Well, we've taken quite a deep dive today into the incredible journey and contributions of Alán Aspuru-Guzik, really guided by those insights from Yorgo Schneepat's essay.
Yeah, it's a powerful reminder that researchers like him, they aren't just pushing the boundaries of technology. They're also really grappling with the deeper questions of how this power can be harnessed for global good and the vital importance of, open, collaborative science.
Absolutely. So here's a thought to leave you with as you go about your day. As quantum technology continues its rapid evolution, how might its increasing power fundamentally reshape our ability, yours and mine, to tackle some of the deepest, most complex challenges facing chemistry, medicine, energy, and perhaps even entirely new fields we can't yet imagine?
Definitely something to think about. Keep exploring those questions.
Thanks so much for joining us for this deep dive. Goodbye.